a non-standard set which, when intersected with the standard model, produces precisely this one. This is an arbitrary choice, there are many. Let's take, for the sake of the example one can always be found, so let's take one. And I take this one, which is quite easy. So this black line is the boundary of the new set. The cusp here is the point 1 plus epsilon square, comma 0. And the two intersection points with the old boundary are 1 comma epsilon and 1 comma minus epsilon. Okay? So it's easy to see that we are not killing any rational point except the point 1 comma 0. That's precisely what we want to kill. Why? Because this little triangle here is 2 epsilon I and epsilon square wide, so it's infinitesimal in size. And this is what we have removed from the set. What we are adding to the set is this yellow area here. Now, the slope of these lines is clearly 1 over epsilon. So these are infinitely steep, and there is no space in there for any rational point. It's very thin, this angle. So we have our set. We want to write this one, the closed set, the black one, in normal form, and see what happens. Just as a reminder, old set, new set. This one happens to be a normal form representing the old set. Why? Well, it's a union of half spaces with just one negative coefficient. So it's what can we do to recover the normal form of the set we are interested into? Well, the naive choice seems to be epsilon is an infinitesimal. Let's put it to 0 and see what happens. If we put epsilon to 0, we don't get a correct answer. Second try. Let's try to be pedantic and expand the definition of the order. So, what it means that x, knowing that x is rational, plus epsilon y, knowing that y is rational, is larger or equal than 1 plus epsilon squared. It means that either the leading term on the left is larger than the leading term on the right, or the two leading terms are equal, and the remaining terms are in the larger or equal relation. Okay? Do the same for the other component. And repeat recursively until we kill all the epsilons. Now we have a formula that represents precisely our set. It has no epsilons in it anymore. Unfortunately, it's not a normal form, it's a very complicated thing. But and those, we might try to apply the Morgan and see what happens, and this is what happens. And that's a normal form, right? It's a union, it's an intersection of one half space and a union of half spaces with one negative coefficient. So it's a normal form. It so happens that this always works. So I showed you two steps that must be taken, expanding the definitions and applying the Morgan. There is a third step that in this example doesn't appear, but after, one can prove that after applying a fixed steps of a fixed number of kinds, if we start with the normal form in the non-standard model, we end up with the normal form in the standard model. Even though, as you might see, the new form is quite different from the old one. The translation is entirely not immediate.
And with all this, you killed 1 point.
With all this, I killed 1 point.
Yeah.
So I represent this set. And this works in general. So in general, you can take any set, embed it into a non-standard model, and modify its border a little bit, but infinitesimally, to make it closed. Then you apply the theorem to the closed set, and you get a normal form. And then you elaborate this, you modify this normal form formally, and you get a normal form.
Do you have to go up to a higher dimension? Do you have to go up to a higher dimension sometimes?
No.
No.
You always get a set of the same dimension.
Okay.
It's the non-standard. You need to actually have precisely districting inequalities.
Sorry?
I think you need this. you need non-standard. So you need
Because of
it's precise to preserve strict inequality. Yes?
in a sense, yes, in a sense, no. So what happens when you go to the non-standard model is that some inequalities which are strict in the standard model can be represented as non-strict inequalities
Yes.
by adding one epsilon. And then over there everything is non-strict, so you can apply the whole theorem.
Yeah, but the thing that because if you take real extension, you will not.
Oh yeah, if you take a real extension, it doesn't, because here we don't care the field structure. We only care the Q vector space structure. So if you take a real extension,
there's no infinitesimal.
yeah. You need this thing works precisely with anything non-Archimedean.
And is the normal form polynomial in size of the original?
Depends on how you express the original.
With binary encodings of all the coefficients and.
So if the original is expressed, I mean, this is polynomial in this. That's true.
Yeah.
This is polynomial in this.
But the original constraints, that semi-linear constraints, you had the affine subspaces.
Well, it depends. If they are given they might be given in a very complicated way with a lot of alternation of intersection and unions. In that case, the thing might explode.
Ah, so it might explode.
But it might explode already by doing the Morgan.
Okay.
That's what I guess, at least. I didn't check. Okay. So we are done with this finite basis theorem, essentially, and we can go to maybe the most interesting part of the talk. We have time for it? So the CSP of topically convex sets, and we want to prove that this object is in an intersected coordinate. The proof is based on this. Essentially, we write these on a finite basis, so then we have to deal only with these finitely many constraints that we know very explicitly. Then we prove a duality theorem for lemma for the specific problems that we are interested into, and then we do something. Duality. Let's look at this little example. So, first of all, these are topically convex sets because it's easy to check that they are max closed. In these three equations define topically convex sets, it's easy to check that they are max closed, and if you add the same constant to all variables, it's easy to check that the equation don't change. So these are topically convex sets. And okay, in general, a CSP for topically convex sets might look like this. Decide whether there is x, y, and z that satisfies simultaneously a list of equations like this. I wrote just 3. Now, what's the naive algorithm of, say, a first-year student that has this to do at an exam? He will probably just consider all possible orderings of x, y, and z. There are n factorial orderings, and each of them gives a linear program. He can solve the linear program. He solves the problem in exponential time, in n factorial time. A smarter student.
This gives you an NP or coherent upbound.
Yeah, which is not very interesting, right?
Yeah, of course.
But it's the NP upper bound, and then I need the co-NP upper bound. That's where the thing gets interesting. A smarter student could try something like this. He could notice that this thing is translation invariant, so it can fix z at 0 and try to draw the sets. So the first set looks like this, the second set looks like this, so this is the intersection. Third set is this one. Oh, there is no point in there. This works, but it's hard to turn something like that into an algorithm. We need an algorithm. And we can find it using this duality. Again, don't try to read the formulas. I'll tell you what it says. We have On, which is the class of those functions in the form that we are, so in this form. Max plus constants, mean plus constants, and averages, weighted averages plus constants. We have the class of these functions, and we consider a vector of these functions. So we have n of these functions, and we want to solve a problem of this form. Find a vector x such that x is component-wise smaller than this vector of function applied to x. Okay?
Can I say this kind of like extension of Farkas lemma?
This looks like Farkas lemma. This looks very like Farkas lemma, with some, yeah.
Yeah, I mean, basically, Farkas lemma means that you don't have max and then don't have mean. And
Yeah.
it's
Yeah.
quite just they have this.
Well, it's not a strict extension of Farkas
Yeah,
lemma,
of course.
but it has some formal similarity. So this is our primal, and we make a dual. The dual is just the same precise statement, the same precise problem with all the equalities inverted. And the domain is slightly different. There is a plus infinity in there, but that's just bureaucracy. Forget about it. The theorem says that one and only one has a solution. So, if we want to prove that P has no solution, we just have to show a solution of D. Let's see in our example how it works. Well, that's a primal of some dual. Then the dual is obtained by taking the very same problem and switching all the inequalities. Now, we know that this has no solution, so we just have to show a solution of that one, and that's easily done. So this is in fact a proof, if we believe the duality lemma, that our primal has no solution. It's a polynomially sized proof. But what if we don't believe that our lemma is true? Then we can prove the theorem. So, let's take our primal and do this simple substitution of variables. So I introduced three new variables, x prime, y prime, and z prime, which are just x. I mean, x is x prime plus 4, and y is y prime plus 2, and z is z prime. And I'm a good student, so I can make the substitution for you. And suddenly, we get a much easier problem, right? Why is this much easier? Well, which of the variables is the largest? X is the largest. X must be either smaller than y prime or smaller than z prime minus 2, so smaller than z prime. So it cannot be the largest, there is something larger. So must be y prime, right? Well, y prime not, because in particular is smaller than z prime minus 1, so it's smaller than z prime. Must be z prime. Z prime is smaller than a convex combination of x prime and y prime. So it must be smaller than one of them. Neither of the variables can be the largest, so there can be no solution. And this is actually the proof of one direction of the duality lemma. So, we want to prove this duality lemma. One direction we see is very easy. Right? We just did it. The other direction is symmetric. So, it's also very easy. The interesting one is the third direction, that one of them has a solution. And this turned out to be proved by using these stochastic mean payoff games in a kind of funny way. How does it work? Again, let's look at our...
Yeah, you can basically like translate this into a stochastic game, because if you look at, for example, Condon's paper, then I mean this kind of system is equivalent to a stochastic game. Then for the stochastic game you have a determinacy, so you just can switch the player. Then you get after switching the player, you get another system like this. Then
and it's symmetric, precisely. Yeah. And how do you read from the solution of these?
This is
how do you read from the solution of the game the solution of these?
So how do you
read from the solution of the game the solution of these?
Solution of the game, solution of this?
Yeah. How are they related?
Well, this is basically if you have that average means that you have this stochastic
choice.
Yeah, stochastic choice. Then -4. No, I mean.
So it's true. What you say is true. So how does it?
By the way, I didn't exactly follow him. So
Okay. You have payoff. Yes.
you have a payoff.
Oh, okay. Then
This constant, but okay. So the idea is this: you have 3 players, which are called max, min, and random, and 3 states, which are the variables in this case. At each moment, the game is in one of the states X, Y, and Z, and what happens is that when the game is in state X, Max gets to choose the next move, and we book a payoff of +2. When the game is in state Y, Min gets to choose the next state, and we book a payoff of +1. Finally, when the game is in state Z, the random gets to choose, and we book a payoff -4. Then we make a long-running average of the payoffs. So you have the value of all your infinite, they play for infinite time, and the value of your infinite game is the limit, the inferior limit, okay, but it's okay, the limit of the averages of the first 10 moves.
And how is the play chosen?
So you start, let's say, from one of the states. For instance, we start from state X. Now the player Max decides what to play, and he might go to state Y or to state Z. If he, for instance, decides to go to state Z, then it's random that chooses the move, and say maybe it turns out Y. So now it's player Min who gets to choose, and so on and so forth forever.
Yeah, I mean, I mean, well, this you actually per se is interesting, but I mean, just to obtain a result, so why not just basically, so here you want to solve this kind of equation, this max-min equation. You just construct a min payoff, or not, stochastic min payoff game. Then you reduce the problem to this
Game.
So this game is going to be in NP equal exact equal NP, so you can obtain that. Solving that.
Yeah, there is a technical problem, however, that this works if you have all strictly less signs here. If you mix some strictly less sign with some less or equal, it doesn't work anymore. You cannot get an equivalent game.
Okay, yeah.
So, in order
understandable.
in order to solve the system, the mixed system, I have to transform it into an equivalent system to which I can apply the duality.
Okay.
But essentially, it is it is mean payoff.
Yeah, I mean, normally it's the other way around. So basically, you want to solve for example, this. Let's forget the mean payoff. This is stochastic games. Then you can come up with this kind of equations. Then you try to solve this equation by then you can solve the game.
Yeah.
Because now it seems that okay.
But I believe that it is interesting to look at the other way around. Why? Because this thing, I mean, at least mathematically interesting. Because this thing is an if and non-if, almost an if and non-if. So if you can prove the duality, which is basically a high school theorem, you have proven the memoryless determinacy for the game.
Exactly.
And you have found a much easier proof than the usual one.
Yes.
I mean, the usual proof of a memoryless determinacy is delicate.
It's not that difficult, I would say.
It's not difficult, but
for example, you can just
since the moment that this guy found the first proof and the moment that these other guys found the first correct proof, 10 years have passed.
Yes, but here they have like concurrent game. They have concurrent game. This means that
no, Gillette didn't have concurrent games. I mean, he proved the theorem only for complete information games.
Yeah. Well, per se, you have.
I mean, for concurrent games, you don't have a memory.
You don't have memories, but you have you don't even have optimal. You have optimal strategies. Yes, right. You're right.
And these works. I mean, all these works precisely because the thing is memoryless and is I mean.
What is infimum over?
Sorry?
So this infimum, what is it over? Infimum over what?
Oh, this is the inferior limit. So it's the limit of the infima. But it is just bureaucracy, because if you take the lim sup, of course you get different value in general, but when the game is played optimally, this is actually a limit. So it's the same thing.
If you apply these memories, this is the problem that if you consider arbitrary strategies, this limit does not necessarily exist. So you have to take limit in for next sup. But actually,
in real world, afterwards it's
afterwards you have just memories strategy to achieve the optimal value. Then the limit does exist. This is just the.
So,
and that's what. So actually the accurate statement is this, that you have to compute the value of false states. It's also interesting how to find the values of the variables from the game, because for instance, if you solve this game, all the states have the same value, which is minus 0.8. So you cannot really read these numbers of 4, 2 and 0 that we had from the value of the game.
Yeah, but that, well, I think it's equally difficult here. So to obtain the value, to obtain the strategy from the value is...
This is not known. It was not known. It is known, but it was not known. So there was this problem. If you have the values, try to find the strategy.
You have the value, yes.
If you have a stochastic mean payoff game and you know the value of all positions, try to find the strategy. It turns out that is as hard as solving the game to core.
Yeah.
So
okay.
having the value gives you no information on the strategy.
Yes.
In general.
Yes. Okay. Yeah.
So you don't see here. So there must be somewhere probability there. Yes. So
Sorry.
Yeah.
So
divide by 2.
The goal of max is to maximize its expected. The expected value of the game. The goal of min is to minimize, and then you look at the expected value of the game when played optimally.
Yes.
And you look at the value of all initial states. So you say, what is this expected optimum if we start from x? And what is if we start from y, and what is if we start from z? If they're all positive, this happens. If there is some negative, this happens. For me it was nice to find that we are trying to solve CSPs, and actually these games come into play. What is interesting now for me, because this wasn't so hard, because you see these games already exist, so it's just applying known theorems essentially. But if you want to add, if you want to do the same thing for all max closed sets, then you have to deal with constraints of the form z is less than x plus 1. And there is no obvious game interpretation of that in the literature. So one needs to build a new game. If the game approach has to work, one needs to build a new game that represents this CSP and prove things for this game. Anyway, thank you for listening. I took the liberty of taking 1 hour because I thought